This is section 4.3, Riemann sums and definite intervals. Riemann sums is the first topic, and it's named after the German mathematician Georg Friedrich Bernhard Riemann. I just have to show off that I can say that in German. Sorry about that. But Riemann is what you call these sums. All right, so looking at example 1. So if you look at the graph of f of x equals square root of x from x equals 0 to x equals 1, and we evaluate this limit as n approaches infinity, where c sub I is the right-hand endpoint of the partition given by c sub I equals I squared over n squared, and delta x sub I is the width of the interval. So notice that for these, the widths are not the same. So this is different from what we've seen before. So don't let that confuse you. In this problem, it's kind of necessary, and this is not something you would have to dream up yourself, so not to worry. Okay, so that's what c sub I is, and delta x sub I is a changing width. All right, so let's first of all find out what delta x sub I is. So if we're going to find the width of the ith interval, which delta x sub I would be, is going to be one side of it, the right-hand side minus the left-hand side, which is going to be one smaller than I. I think I said that backwards. I would be the right side, I minus 1 would be the left side. At any rate, this difference is going to simplify nicely. Let's see if I can do this in a few seconds. This will be I squared minus 2I plus 1. And then subtracting the two fractions by collecting like terms. I squared minus I squared is 0. 0 minus negative 2I is positive 2I. And 0 minus positive 1 is negative 1. So that's what delta x sub I is. So our limit that we're looking at as n goes to infinity of sigma I equals 1 to n of f of c sub I times delta x sub I. And by the way, before I get very far from this idea and too deep into this problem, the widths don't have to be constant. The reason we made delta x be minus a over n is that algebraically that's the easiest thing to do. So what you're seeing here is an example of, you really don't want to have to do this, where delta x is not a constant. It makes it really difficult algebraically to deal with. So doing the substitutions into this, the function was square root of x. So this will be the square root of I squared over n squared, because that's the square root of c sub I, multiplied by 2I minus 1 over n squared. So the simplification makes this I over n times 2I minus 1 over n squared. So I can bring the constant for sigma. N is considered constant. So I'm going to bring the n times n squared in the denominator out in front, making that 1 over n cubed. And then distributing the I, that's going to be 2i squared minus I. All right, and then using the formulas that we have, pulling out the 2, and first separating, make this sigma of 2i squared minus sigma of I, then pulling the 2 out in front. This will be 2 times sigma I squared. If you recall, that formula is n times n plus 1 times 2n plus 1 all over 6 minus sigma I, and that formula for sigma I was n times n plus 1 all over 2. Okay, so that's going to be 1 over n cubed times, let's see, the 2 over 6 will reduce to 1/3, and n times n plus 1 times 2n plus 1 is n squared plus n times 2n plus 1 minus, and don't forget that 1 over n cubed. I'm actually distributing it in this step. And I'm going to make that 1/2, pull that denominator out, and n times n plus 1 is n squared plus n. Okay, so we have the limit as n approaches infinity of 1/3 times 1 over n cubed times 2n cubed plus n squared plus 2n squared is 3n squared plus n minus 1/2 times 1 over n, 1 over n cubed times n squared plus n. So this is the limit as n approaches infinity of 1/3 times 2 plus 3 over n plus 1 over n squared minus 1/2 times 1 over n plus 1 over n squared. So we're ready to do the limits. The limit of the constant 1/3 is 1/3 times the limit of the constant 2 is itself, 2. The constant's limit is itself. The limit is any constant over a power of n goes to infinity. That becomes 0. So that's 0 minus 1/2 times 0 plus 0. And this ends up being 2/3. Okay. So, if we look at that picture, of the graph. Sorry, I'm moving this thing and I hate to talk and do something at the same time because you've heard me mess up several times when I do that. So in other words, if this curve from 0 to 1 of the square root of x we're stopping at 1. And of course, the square root of 1 is 1. And so that makes a square that's 1 by 1. And of course, the area of that square is 1 times 1 is 1. And if we found out that the part below the curve is 2/3, that of course implies that this part up here has to be 1/3. The total area 1 minus the area underneath the curve 2/3 leaves 1/3. Okay. So, the Riemann sum can have unequally wide partitions. And we're not going to deal with that much, but it is a possibility. So what can happen if you allow for different widths is, let's say that you have some function from A to B, and you have unequally wide intervals. If my first subinterval went to here, and I used a right-hand rectangle, and then I had infinitely many rectangles in here, is it sufficient to make n go to infinity? Well, the part between, let's call this C, the part between C and B with infinitely many rectangles would actually become the area exactly, but from A to C, we would have that error. Our rectangle is slightly too big for the curve. And so, even though we have infinitely many rectangles, the error that we're making from A to C would make the answer from A to B not be true and correct. So, if you're going to have unequally wide intervals, we have to have the width of the largest subinterval approaching 0. Okay? So, the width of the partition, the norm of the partition, is it the width of it? We want that to head towards 0. And that would take away this particular problem we saw here, because if all the widths are headed towards 0, even if they're unequally wide, if we have infinitely many of those, and the widest one is headed towards 0, then it will exactly capture the area. So sometimes you'll see theorems that use, instead of n approaching infinity, which is actually fine as long as you have equal subintervals, where delta x is b minus a over n, where they're always equally wide, it's sufficient to say n approaches infinity. But technically we should be saying the norm of the partition is approaching 0. So if you look at the definition of Riemann sums, notice that there's no clear expectation that delta x has to be consistently wide. So that means that we have a more robust definition than if we limited ourselves in the situation where delta x is always b minus a over n. So theoretically, it can be a partition of unequal widths. So if you read that, notice they don't say delta x is b minus a over n. They define delta x sub I as the width going from x sub I minus 1 to x sub I. And c sub I is any point. By the way, that's another point of clarity. We use the right-hand rectangle when we did this, because algebraically it was the simplest. But you could actually have that C sub I be anything, and it could change from partition to partition. For the first rectangle, it could be the left side. For the second one, it could be the midpoint. For the third one, it could be a 16th of the way from left to right, whatever you want it to be. So this is a very robust theorem because it allows for every possibility. And at any rate, the Riemann sum is the sum of the f of C sub I, which would be the height of the rectangle, f of C sub I, multiplied by the particular width that time, delta x sub I. And that's what we call a Riemann sum. Basically the sum of a bunch of areas of rectangles. And as we said before, we've made it algebraically simpler ourselves. So if we indeed have regular intervals, this is what delta x will always be for all rectangles. And that's where we're actually going to stay. We're going to stay with that idea. Well, I'm not going to make you do the unequally wide ones like that first example. If we take this equation where the norm of the partition, if that were equal to b minus a over n, we could, not equal to, my bad, let me take that back. If we made the width of the partition greater than or equal to delta x, so that if you used a common width, if the partition is bigger, the norm of the partition is bigger than that, and we multiplied both sides by n, and n is positive, so the inequality will not change direction, and then divided both sides by the norm of the partition, like this. That would mean that we'd have to have a number of rectangles that's greater than or equal to b minus a over the norm of the partition. As the number of subintervals in a partition approaches infinity, as n approaches infinity, that will happen only as, for this to approach infinity, b minus a, which is a constant, over the norm of the partition, that would mean that the norm of the partition itself, not the fraction, but the norm of the partition itself has to go to 0. So b minus a constant divided by something really close to 0 gives you an infinitely large answer. The converse of that isn't true. In other words, you can't say that, let's see, our statement is, let me make sure this is clear. That is, the norm of the partition approaching 0 implies that n approaches infinity. The converse of that statement would be n approaching infinity implies that the norm of the partition has to go to 0. And if you look at the picture I drew above, that's not necessarily true. In this picture up here, from C to B, I had infinitely many rectangles. But this A to C one isn't changing just because there are infinitely many from C to B. This one's not changing, and that norm of that partition is the width from A to C. That's the largest width you have, and it's not changing. So this is not necessarily true. This statement here, the converse of that statement, is not necessarily true. All right, so now I'd like to move to something called the definition of the definite integral. If a function f is defined on the closed interval from a to b, and the limit of Riemann sums over the partitions delta, the limit as the norm of the partitions goes to 0 of sigma of f of c sub I times delta x sub I exists, then f is said to be integrable on the interval from a to b, and the limit is denoted by this symbol. So I'm not going to write the left-hand side, but this is the integral from a to b of f of x dx. Okay, and so what's happened is that limit and that sigma together have combined to give us that integral sign, which is this kind of S-looking thing, which I think we've seen before. Think about that. We'll make a connection between what we did before and this very soon. The f of c sub I became f of x here, and the delta x sub I became dx right there. Okay, this limit is called the definite integral of f from a to b. The number a is the lower limit of integration. It's on the lower part of the sigmas of the integral sign, and b is called the upper limit of integration. It's on that top part. Though Riemann sums were defined for functions with very few restrictions, a sufficient condition for a function f to be integrable on the interval from a to b is that it is continuous on the interval. So theorem 4.4 says that if f is continuous, then f is integrable, and therefore the definite integral from a to b of f of x dx exists. So continuity is a very important restriction, and so when you get into calculus 2, we'll have to deal with, well, what if it's not a continuous function? What does that imply? That's something for Cal 2. So for right now, f has to be a continuous function, otherwise you cannot evaluate a definite integral if continuity is broken anywhere between a and b. Of course, it'd be continuous beyond that or before that, but between a and b it has to be continuous. Very, very important. All right, so we're asked in our example 2 to evaluate the definite integral from -2 to 1 of 2x dx. Okay, so the function f of x equals 2x is integrable on that interval because that polynomial function is continuous for all reals, which means it's definitely continuous from -2 to 1. For our convenience, as I said before, the delta x sub I that we're going to use is going to be what we call delta x before, and we're always going to use this and make this b minus a over n. Okay, so 1 minus -2 over n is 3 over n. And again, if we use c sub I is a plus I times delta x. It's the formula I gave you. I think I called it x sub I. Doesn't really matter. It's the same idea. So a is -2 plus I times delta x, which is 3 over n, And again, we made these choices to make our work as simple as it could possibly be algebraically. And this is going to be pretty messy regardless. So make sure that you know these definitions. Delta x is b minus a over n, and c sub I, or if you want to call it x sub I like I do, is a plus I times delta x. Those are very, very important formulas to know. So let me put a little indication that those are important again. I think I said this once or twice before, but it doesn't hurt to reiterate that point. All right, so now we're ready to find this definite integral answer. So this is going to be the limit, according to the definition, as the norm of the partition goes to 0 of sigma from I equals 1 to n of f of c sub I. This is the formula for every definite integral, by the way, that I'm writing now, not the specific one for this problem yet. So, more specifically to this problem, because we decided to use delta x, and all of the partitions are equally wide, we can say that's the same thing as having the number of rectangles go to infinity. For the norm of the partition to go to 0, for us, that means that the limit that we find will be as n approaches infinity. And so this will change to become, instead of delta x sub I, it's just plain delta x. And I'm going to say that from now on, you can go straight to this. I was just trying to apply it to the theorem so that you would have an idea of the connection between it and what we're going to be doing, is that connection I just made. Okay, so now let's do the specific problem. That second line that I have an arrow pointing to is kind of a formulaic thing that you should know, that that's how you set it up. Okay. Now our function is 2x, and so I'm going to put in to the function, which is 2 times x, I'm going to take the c sub I out and put in its place what we calculated c sub I to be, which is negative 2 plus 3i over n. And I'm going to replace the delta x with what we calculated above, which was 3 over n. Okay, so the multiplication of 2 and that fraction at the end makes it 6 over n, and both 6 and n are considered constant as far as sigma is concerned, because the variable of sigma is I. So I'm going to pull that 6 over n out, leaving inside the negative 2 plus 3 over n times I. All right, so applying some of the properties of sigma to this problem. The sum in the formula means that we can split this into 2 sigmas. So this would be sigma of negative 2 plus sigma of 3 over n times I. I'm going to go ahead and use another property and pull that constant out in front of the sigma. 3 over n is considered constant as long as the variable of sigma is I. That will be something that we can do. So this will be 6 over n times. Now, if you recall, the sigma of a constant is that constant times the number on top of sigma n. Okay, and then the formula for sigma I is n times n plus 1 divided by 2. Okay, so distributing the 6 over n through, that will become negative 12 plus 18 over n squared multiplied by n squared plus n over 2. (18 over 2 reduces to 9, and then distributing n squared over n squared will be 1, plus n over n squared will be 1 over n. And the limit of a constant like negative 12 is that constant, negative 12, plus 9 times 1 plus 1 over n as n goes to infinity heads towards 0, and we end up getting an answer of negative 3. All right. If we were to graph this function and look at it and see what it is that we've actually accomplished, we would see a graph of this function looking like this. It's y equals 2x, and we're going from negative 2 to 1. And notice that the integral answer that we got does not represent the area of the region. In fact, definite integrals can be positive, they can be negative, or they can be 0. So for the definite integral to be interpreted as an area, the function f must be continuous and must be non-negative on AB. So let's see what happened here. This is a width of 2. 2 times negative 2, this is at negative 4. And so if we multiply 2 times negative 4, we get negative 8. And then two times 1, this would be 2. Oh, I'm sorry, I messed up. I forgot to multiply by half. There we go. 1/2 base times height. So base times height, 2 times negative 4 is negative 8, times 1/2 is negative 4. And this is a height of 2, as I said earlier. So 1/2 base times height, 1/2 1 times 2 makes this 1. And so the sum of negative 4 and 1 is how this is equal to negative 3. So the sign of y actually does have an effect on the answer you get for what we might think of as area. It's actually the area of that lower triangle is 4, but it's got the sign on it of negative because the y value that helped create it is a negative number. So moving on to the next page, the definite integral, theorem 4.5. If f is continuous and non-negative on the closed interval from a to b, then the area of the region bounded by the graph of f and the x-axis and the vertical lines x equals a and x equals b is this. The area is the integral, definite integral from a to b of f of x dx. This is only true, keep in mind, this is only true if f is non-negative. And that's a very important declaration. And so you can see why this answer of -3 is not necessarily the area of the region, because how big is that region actually? What is the actual area between that line and the x-axis? Well, this one has an area of 4 and the other triangle has an area of 1. The actual area enclosed is 5, but the definite integral gives us -3. So we have to be very careful that that non-negative part of the graph is not interpreted as area. We actually have to take the opposite of that definite integral answer for that part, make it +4, and add it to 1 to get the area. So it's something that you need to be aware of. Okay, so let's look at the function f of x is equal to 4x minus x squared. That's a parabola that opens downward, and I'm factoring so I can get the x-intercepts. So the x-intercepts for this graph are 0 and 4. And it opens downward. Because of symmetry, I know that the vertex is somewhere, well, it's exactly halfway between 0 and 4, so it's at 2, and the y value of that is, I'm just going to say it's there. So here's the part of the parabola that we're interested in for this problem, and we're asked to find this area. So the area, or I think it asks us to, it doesn't ask us to do anything specific, I'm sorry. All right, so the area here would be the definite integral from the x-coordinate where the region starts, 0, to the x-coordinate where the region ends, 4, of the function f of x minus x squared dx. Because it's non-negative from 0 to 4, that's a correct statement. Now, there are two ways we could proceed here. We could use the limit definition, or we can check to see if this definite integral actually represents the area of a common geometric region, such as a rectangle, triangle, or semicircle. So if you look at the picture I did above of that line, that was two triangles. And notice how I was able to get the area using geometry. Of course, it was non-negative. Not non-negative, so that doesn't quite apply. But if this parabola had ended up being like a semicircle, then I could have found the area of the circle and divided it by 2. In this particular case, we would not get a nice geometric figure that could easily find that, and so find that definite integral, which would be the area. So we'll come back to this one, or one like it, soon. So let's do some where we can actually use geometry. These are going to be kind of a small subset of all problems can be done this way, by the way. So if I were to graph y equals 4, which is this function, y equals 4, this graph right here, and And that's non-negative, so we can interpret the integral as the area from 1 to 3 below that function. And so let's mark off where 1 and 3 are. And so the area we're talking about under the curve from 1 to 3 is the area of that rectangle. And of course, since we know how to find the area of a rectangle, we can evaluate this definite integral using geometry. So let's see, how tall is that rectangle? Well, it's always 4. And from 1 to 3 is a distance of 2. And length times width gives us 2 times 4, which of course is 8. Okay. B. By the way, could you do that for any constant function? Yeah, that would not be too hard to do. Not too hard to interpret at all. Okay, x plus 2. Integrated from 0 to 3. So let's look at that graph. X plus 2. Okay. Is a line whose y-intercept is 2 and whose slope is 1, so go up 1 over 1, up 1 over 1, up 1 over 1. And we have that line. Pretend like that's a nicely drawn straight line. And we are integrating from x equals 0 to x equals 3. So we want the area of that region. Well, that's a trapezoid. I know you're used to seeing trapezoids written this way. A lot of times they're drawn in this orientation where the bases, which are the parallel sides of the trapezoid, are horizontal, but they don't have to be. Here, the x equals 0 and x equals 3, those are the bases of the trapezoid. So it's kind of an uncommon thing that you're going to have to get used to seeing. But anyway, if this is called base 1 and this is called base 2, you should know the area formula for a trapezoid is base 1 plus base 2 times the height of the trapezoid, which I haven't labeled yet, divided by 2. The height is the perpendicular distance between the bases. So the perpendicular distance between the bases. So in this particular problem, the distance between bases is 3 units. So that's what h is. And base 1 is the height here, so that's 2. And this one is 5. So using the formula for the area of a trapezoid, that's going to be 2 base 1 plus 5 base 2 times the height, which is 3, divided by 2. And so 21 halves is the area of that region, which means that's the value of the definite integral from 0 to 3. Okay, C. C asks us to do the integral from -2 to 2 of the square root of 4 minus x squared dx. So we're hoping for a nice figure whose area can be found using geometry. This one's a little bit harder to see because you're not used to seeing the equation in that form. A lot of times we don't like radicals. If we can get rid of them, we do. So if I were to square both sides, I could get rid of the radical. But do keep in mind that before we started with y equal to the square root of something, that means y is always going to be greater than or equal to 0. Okay, so keep that in mind. And then if I add x squared to both sides, I get the equation of a nice circle. So this is a circle that's centered at 0, 0, whose radius is 2, the square root of 4. And the circle would go all the way around with a radius of 2, like that. Now, keep in mind, we can only use y that's greater than or equal to 0, so the actual graph that this one is referring to is the top half of that circle, so this semicircle, and we're finding the area under that curve down to the x-axis between -2 and 2. So you all know, I hope, that the area formula for a circle is pi r squared. So the area of this circle is pi times 2 squared, so 4 pi. But we're actually interested in the semicircle area, so this definite integral is 1/2 multiplied by the area of the full circle, and so that's 2 pi. Right. So those are not too bad. And when you can get a geometric figure and find the area using formulas you already know, that's a good plan. All right, we're going to stop here, and I'll continue in the next part.